Let's talk about rotation matrices and homogeneous transformations. So when you're working with a robot like this, it may be doing a series of arbitrary maneuvers, and you want to be able to keep track of the end tip position and the end tip orientation. Now, in a typical setup, it's not very convenient to directly measure the end tip coordinates. You can, of course, use a camera with a vision system to do that, but it is not always practical in every situation. So, the more common situation is you know at every joint the angle, and from that you try to infer what is the end tip position and end tip orientation. So imagine there is a coordinate frame that is attached to the end tip, and for any given joint configuration, you need to be able to know the exact orientation of this. This is just trigonometry. You can, of course, draw a bunch of triangles, apply a bunch of trigonometric identities, and calculate that. But you don't want to do that for every new situation and every new configuration. So you want a fairly generalizable mathematical framework that you can just blindly apply in an algorithmic way, write it as a piece of code, and that will do your work every time. So that's where rotation matrices come in. Rotation matrices, they are nothing but a simple mathematical framework that helps you calculate your orientation no matter where you are in your robot configuration. And when you take into account the specific distances and you want the end tip coordinates, there you get into homogeneous transformations. So that's what we will do next, rotation matrices and homogeneous